Okay, so today we're going to look at Newton's law of cooling, and it's going to feel very similar to yesterday's lesson when we were talking about exponential growth, but now we're going to talk about cooling, which is a little bit like decay, but not quite the same. Uh, Cooling is going to be a little bit different. Before we get into the note, though, I want to ask you this question, and you can pause the video if you want and discuss with the class. But the question is, what freezes quicker, cold water or hot water? So if you need ice really, really fast, as you can, would you take your ice cube tray and fill it with cold water and put it in, or would you put it hot water in and put it in? And you can pause and debate about that. So the answer actually is you would put hot water in. And there's a very good science answer to that. But essentially it has to do with Newton's law of cooling, that something will cool quicker if the difference between the outside temperature and the inside temperature is bigger. It'll freeze faster. It has something to do with momentum of particles as they freeze and they slow down and things like that. But right now we're going to investigate the math of that idea. So Newton's law of cooling says this. States that the rate at which a body cools is proportional to the difference between its temperature and that of the surrounding medium. So if we were to consider the ice freezing or the water freezing, when you put hot water into your freezer, then the difference is pretty big between that hot water and the cold air, the surrounding medium of the freezer. And so the rate at which it freezes is going to be quicker. Whereas if you put something that's already really, really cold and you put it into the freezer, it's not going to freeze as fast as the hot water. So this is similar to yesterday's idea or last lesson's idea, because in that one we talked about exponential growth was relative to its size. Here, this is just a different relativity. It's relative, the speed at which this grows or cools will be relative to the surrounding temperature. So because of that, the two concepts are very similar with one small change. So in this case, the formula to find the T, the temperature of the actual item, will still be that C times e to the kt from yesterday, but here you have to also add the surrounding temperature. So when we describe the temperature of an object, there are actually two things that we're considering. Not just the temperature of the object itself, but the surrounding temperature. So if something is actually 15 degrees Celsius, part of that 15 degrees Celsius is the surrounding temperature of maybe 10 degrees, and then the object itself is 5 degrees. So we have these two variables. So T being the body temperature, the actual temperature that we consider, is made up of C to the E, or C times e to the kt part, plus the surrounding temperature.